start. So good afternoon, everyone. Welcome to this NITheP colloquium. My name is Francesco Petruccione, and it is my pleasure to introduce today Professor Gershon Kurizki. Gershon is the G.W. Dunn Chair in Quantum Optics at the Weizmann Institute of Science since 1998. Yeah, and many of you might know him because of his important contributions to quantum thermodynamics, open quantum system, quantum optics, and quantum light matter interactions. Yeah? He has published hundreds of papers with a very high age index of, I don't know if he's older than his age index or younger, but it's a very, very high age index. And he has been recognized by many societies. He's a fellow of the Optical Society of America, of the American Physical Society, of the UK Institute of Physics. He received the Lamb Award in laser physics and quantum optics in 2008, the Humboldt-Meitner Award in atomic physics in 2009. And he doesn't publish only science paper, he also publishes philosophical essays and poetry. And very recently, he's published a popular science book with a very interesting title, The Quantum Matrix. And just this morning, I received my copy. I need to pick it up from the bookstore. Yeah. Gershon, we are really very happy that you are with us today. And we are really looking forward to this talk that has a very exciting title. Yeah. And sorry, before I ask you to start, Gershon, sorry, let me just tell the participants that Camille Lombard-Latuna, who's a postdoc in my group and who has worked previously with Gershon, will take over the role of moderating the question and answer session at the end of the talk. So please, if you have questions or comments, make use of the Q&A facility at the bottom of your Zoom screen. So Gershon, now your first slide is already up. Please, you're welcome to start. And again, thank you very much for being with us today.
Thank you very much, Francesco. I'm happy to be back here in Durban, albeit not in person, but that's the best we can manage these days. And I hope that I'll be able to convey some of the messages that I have in mind, which are dedicated to the question that is probably the most profound question of science and of human thought in general, and that is, what is the rapport between us and the world that we perceive or observe? Now, since observation provides the data for science, the input for science, the equivalent question is, does science describe the universe or does it not? Okay, and that's a non-trivial question. I would like to dwell on what I find to be the key approaches to this question in science and culture, and on some of our own contributions to clarifying this question. And you will find more on that in the book that Francesco just mentioned, The Quantum Matrix, that was published by Oxford recently. So, I would like to start with this painting, Las Meninas by Velázquez, because it has something curious that not everyone notices, and that is that the painter is in the picture in a posture which cannot be true, because he should be painting the picture, but that's not what his posture is like, okay? And since Velázquez obviously knew his trade, he was trying to tell us something by this. And to me, this represents the dual stance of the painter or the observer in general being part of the scene, but also its creator, okay? So this is in a nutshell the problem that I would like to address, this rapport between the observer and the world. Now, the first discussion of this problem, to my knowledge, is by Democritus of Abdera, that has this conversation between the senses and reason. Now, the senses say there is smell, there is color, there is taste, and reason retorts there are only atoms and void. But the senses then reply, you owe everything to us, and then you discard us? Now, mind that Democritus was the father of atomism, so obviously he thought that it is true that only atoms and void exist. And yet he points out that if you discard or doubt the sensory input, then the reason hasn't much to go by, okay? Nothing at all, in fact. And therefore, there is an inconsistency in this rapport between the two. And this inconsistency is, in fact, inherent to science, because what science has, no matter what you think about, is some kind of combination of observations and reasoning about these observations. There is nothing more. And the question is whether it is possible to reconcile the two in a reliable fashion and deduce the true essence of the world through that. Well, not according to Kant, whose influence had been overwhelming until recently. He thought that the world is unknowable in principle, Ding an sich, the thing in itself. And he thought that science can only perceive the world through our innate categories of thought, which to him were the Newtonian space-time and causality, okay? So he thought of these as the absolute truth. But now we know better. We have relativity and quantum mechanics. So is there still an absolute truth that we can cling to? And Eddington, who was a great proponent of Einstein, thought that that was not the case, that in fact, there is no absolute truth left. And he illustrated this in his excellent book by the following parable about an ichthyologist, a fish researcher, that throws his net into the ocean, and then he looks at his catch and concludes that there are no fish smaller than 1 inch. And then someone remarks, but the mesh of your net is 1 inch. So how can you expect to catch a smaller fish? And the ichthyologist replies, fish that cannot be caught by my net are to me metaphysical, and I have no interest in them. So what Eddington was trying to tell us is that it is inevitable that we have mental filters through which we perceive the world. But as long as we are aware of that and are able to, in some sense, correct or shape these filters, we can achieve progress in science. There is a more skeptical view of the world by Ernst Mach and the Vienna Circle in the late 19th century, called positivism. And to them, the world is but a stream of data. We have absolutely no notion of what's behind these data. All we can do is try to interpret them. And that is why he objected to atoms, because they were not observable, okay? So it is striking that the only great scientist of modern time that held the view that science is really about the world and reveals some objective truth, which is observer-free. He called it realism. So Einstein was really an exception in this respect. All others before or after him were not of this mind. So who is right? Well, before we pass judgment, let us consider what is meant by observation in science. Now, scientific observation as we know it today goes back to Galileo, that revolutionized science and overthrew Aristotelian science that existed before by making observations that approximate or idealize what is perceived by singling out one aspect in an experiment and discarding all the rest. This kind of idealization is Platonic in spirit, and that was Galileo's great contribution. And so this is, I would say, put very bluntly by Rutherford, that said there is physics and there is stamp collection, by which he meant that all other branches of human knowledge, except for physics, really deal with superfluous detail, and it is only physics that focuses on the essential. And since this means that observation has to be goal-driven and approximative, this means that it is not merely a recording of reality. It is more a kind of stylized painting than photography, if you like, to image. Now, the role of the observer, which was already, I would say, somewhat enigmatic before Boltzmann's time, became even more so when Boltzmann introduced the time arrow. This is a notion that that Eddington coined, but it relates to Boltzmann's work, which is an attempt to interpret the Clausius second law by stating that the entropy of the world grows, and this in later formulations, well after Boltzmann, means that information decreases or ignorance grows. Okay, and you can apply this principle not just to the world as a whole, but to isolated macroscopic systems. But the question which remains moot is, whose information are we talking about? Does information and the time arrow have any objective meaning? Which would be odd, because information appears to be a human anthropocentric notion rather than an objective notion. Or in other words, why should nature care about information? But that was Boltzmann's way of explaining how come a glass that falls off the table and is shattered cannot reassemble itself and jump back to its original state, which it would if time arrow did not exist and time were reversible. And yet his contemporaries, notably Poincaré and Loschmidt, thought that this was wrong, and that time is fundamentally reversible. Now, the notion of an observer came to the fore in thermodynamics even before Boltzmann, when Maxwell introduced his demon that can reduce entropy by sorting out molecules according to their speed, say in a partition of a container. And here you see Gamov's caricature, which shows that water is separated into ice and vapor by observation. Okay. Now this seems to go against the second law, and it can be even aggravated by considering the scenario that Szilard had in mind in 1926, where he showed that by observing atoms in part of a container, okay, you can commute this information into work that is extracted by the observer. So that means both these illustrations tell us that information has physical meaning and not just mental meaning. It cannot be treated as merely mental category. Now, it was Landauer in *58 that showed explicitly that one should treat the demon as a thermodynamic resource, the memory of the demon as a thermodynamic resource, if you want consistency with the second law, and the price that you pay for all these operations is the erasure of information from the demon's memory after each operation. And yet, it is undeniable that in all these cases, the observer plays an active and physical role merely by observing a physical system. And this became even more scandalous in quantum mechanics, because very early on, both Max Born and Niels Bohr recognized that quantum mechanics is just a measurement theory, okay, nothing else. It's not a theory of reality, it's a theory of measurements, which means that observables and their uncertainty are determined by the setup or by the contextuality that are chosen by the observer. And Niels Bohr had formulated the principle of complementarity that relates the uncertainties of non-commuting observables, thought that this principle holds a deep philosophical truth, namely that the constraints on the information that we can extract from measurements are inherent to the process by which our mind acquires knowledge or information. And anything beyond those constraints was to him unspeakable. But he never explained why is that. It remained quite a mystery, I would say, to this day. And it was the essence of quantum mechanics as measurement theory that motivated von Neumann to formulate the theory of quantum measurements, which was based on the projection postulate, whereby you cannot perceive a superposition of results, only one possible outcome at a time corresponding to one eigenstate. So if you have a photon in a superposition of reflected and transmitted states, you can perceive either the reflected photon or the transmitted, but not both at once. And von Neumann and his friend Wigner were of the mind that this happens in the observer's mind, this projection, because our mind is incapable of perceiving superpositions. Otherwise, the mental states of the observer would be correlated to the eigenstates of the quantum object, okay? And they did not think it was plausible, but this doesn't rule this possibility out. Perhaps this is exactly what happens, yes? Now, here you see my younger version debating this issue with Wigner. I cherish this photo very much. It's quite a memento. Now, Everett had a different interpretation, whereby it is the observer that, by making observations, creates parallel worlds. In other words, the possible outcomes of a measurement of a superposition state are materialized in different worlds. And in principle, you may say that a tiny quantum effect, such as whether the photon is detected or not, may trigger a chain of events that would really make these worlds distinguishable. For example, if the photon is detected, the observer is happy, and this story ends with a happy ending. But if he does not detect the photon, he is upset, and this story ends with his suicide. Very tragic. And since quantum observations occur at a staggering rate, you will have an enormously complex web of worlds developing as a result of these incessant observations all around us. And in some of these worlds we exist, in others we don't. What is curious is that Everett was not the first to come up with this fantastic, outlandish view of the world. Borges, the great writer and thinker, has a story in which he discusses the following. A web of bifurcating, crisscrossing times exists, and it encompasses all possibilities. In most of them, we don't exist. So it's really one-to-one Everett's view of parallel universes. But Borges, who was no scientist, said that before. Now, what I would say Everett's interpretation glosses over, otherwise it is perfectly consistent as interpretation of quantum mechanics, but what it glosses over is the element of choice, because obviously to create worlds or not depends on the choice of the observer, which measurements to perform and whether to perform. And this may end up in your existence or inexistence. So it's quite a strange mix of freedom of choice and determinism. And there was a Jewish sage in the 2nd century, Rabbi Akiva, that might have referred to the same scenario in his words, that all is predetermined, but the license is given. So quite paradoxical. And this is, if you like, the status of the observer in quantum mechanics. Now, obviously, most physicists were unhappy with such issues, trying to avoid them. Certainly Einstein was. His reason for formulating relativity was that he wanted a theory that is equivalent for all observers. But how to accomplish that in quantum mechanics? So quite a few physicists thought that the environment can do it for us. It can objectivize quantum mechanics. And this means that superposition states always must decay to a statistical mixture of what Zurek called n-variant or pointer states that are robust against the effects of the environment. And this process is essentially irreversible, so coherence and quantum information are lost to the environment and cannot be recovered. Well, we disagree. In the first place, the environment does not really kill quantum coherence or quantum information, because you don't have to stick to a particular set of pointer states. There is an infinite choice. You may choose pointer states which are not robust against environmental effects, and yet this basis will hold nearly all information about the quantum observable, which is measured, and you can recover this observable by generalized measurements, so-called POVMs in jargon, but in principle, under very mild conditions, this is true. Almost nothing, I would say, is completely lost due to the effect of the environment. So this is the first ground. But the second ground is that even when the environment devastates quantumness, the observer can override its effects. All right? And this is what I would like to show you. So here is a story from our book, which is meant to demonstrate that, let me go back, that equilibration with a heat bath depends on observation and can cause heating or cooling. The hero of our book, Henry Barr, who, thanks to a gadget that he invented, acts as a quantum object, is about to be burnt alive by accident, but he is saved by his competitor, Eve, who measures his energy at the right rate. Now, what is the right rate? She asks him, how frequently, darling? And he says, as frequently as you can, use Zeno. And when she does, things get worse. He's heated up even more and says, I'm being scorched alive. What's wrong? And she knows better, and she says, I'll reduce the rate. Zeno isn't the answer. And she reduces the rate, and he says, right, now I'm chilling off. And she says, see, the solution was anti-Zeno. Okay. Now, he explains these effects by saying that the fire interacts with me, and therefore we become entangled. But if I'm measured, and here I want to stress that by measurement, I don't mean the actions of a Maxwell demon that really has to read out the measurement results. You don't have to. It's enough that you just single out by your measurement the object that you're trying to measure. And this disentangles the object from the environment. And as a result of this disentanglement, energy is released as heat, okay? So if you measure too frequently, you are progressively heated up. But if, on the other hand, you adjust the rate and you measure at the rate that Eve was using in her measurements, the heat energy is transferred from the object to the bath and the object is cooled off. So I would say that's a pretty active effect. Now, you may think that this is science fiction, but we actually did the experiment. in which the object, Henry, was a carbon atom, and the environment, the bath, consisted of 3 protons. And by measuring the carbon at the right rate, we cooled it down, okay? Whereas if the rate was much higher, the measurements heated it up, okay? Now, so at least temperature and equilibration are observation dependent. But we contend that much more can be done. And in fact, we are planning experiments to prove that. What we say is that it should be possible to reverse the time arrow of an open system, okay? And that would be quite striking. The classical analog would be that instead of a pendulum that represents the system, which is coupled to a collection of pendula that represent the bath, each acting independently and picking up its own phase and energy, you could make the bath pendula act in unison so that the process becomes reversible. All right? And quantum mechanically, you can think about a 2-level system coupled to a bath in which normally you expect coherence to decay irreversibly, as shown here as a function of time. But if you act on the bath and manage to purify it, which is possible, we contend, even though the bath is infinite, then you may restore your coherence, make it the same as it was initially, corresponding to a reversible process. Well, in the practice, it will not look so clean as here, but you will be able to see some revivals of your coherence as a result of acting on the bath. And grosso modo, this would mean that you manage to, at least to some extent, reverse the time arrow and make it dependent on the control and observations performed by you. And that would, if and when this is demonstrated, we are really serious about doing such experiments, then we would go against the established maxim that time is unidirectional. This maxim goes back to Heraclitus of Ephesus, that even was somewhat before Democritus in the 5th century BC. And his maxim was pantare, everything flows, or as it is more colloquially known, you can't bathe in the same river twice. So one of my poems in the book says that this need not be true. Everything flows, Heraclitus wrote, what's now here is never to return, but our science is challenging this quote. At small scales, everything can backward turn. Imagine how life will change if we can find ways to revert the little time flow, when happy flames extinguished in our mind will be rekindled in their old warm glow. And so, in principle, quantum mechanics has this possibility of reverting the time arrow. There is a better known effect of observations, and that's the Zeno effect, which is based on Zeno's error paradox. Zeno's claim was that the observation of motion is an illusion. And his argument was that in order to reach the target, the arrow has to cross the midpoint, and to reach the midpoint, it has to cross a nearer point, and so on and so forth, until you have to consider just a single point at which the arrow is located, and that means that the arrow cannot move. Motion is a logical impossibility. Now, there is a related paradox, that of Achilles and the turtle, in which Achilles gives the turtle a head start, but is never able to catch up with it for the same reasons as here. Now, Aristotle tried to bury these paradoxes quite successfully, and people have almost forgotten about them. And in the 19th century, with the advent of mathematical analysis and the concept of infinitesimal limit, it became sort of clear that these are naive arguments that do not hold mathematically. And yet, in 1978, Misra and Sudarshan revived these paradoxes, the quantum, the Zeno paradox of the arrow, by introducing what they call the quantum Xeno effect, which was first demonstrated by Itano et al. And since then, there have been many observations of this effect. Now, we generalize this notion to open systems by pointing out that time energy uncertainty is the key to the quantum Zeno effect in an open system. A level which is coupled to its environment is broadened by frequent observations, and this broadening can suppress the coupling to the environment. So if you plot the rate of decay of an observed state as a function of the rate of observations, you expect to see a decrease, okay? And that would be the quantum Zeno effect, corresponding to progressive broadening of this level. But we showed that the opposite is also universally true, that if you observe at a somewhat slower rate, so that the broadening is not so overwhelming as here, then you get the opposite effect, that decay is accelerated by increasing rate of observation. As you can see here on a logarithmic scale, that the decay rate increases with the rate of measurements. And this we call the anti-Zeno effect. And this would mean that when Zeno expects the arrow not to fly, he may be in for a surprise that the arrow actually flies even faster than one could have thought. Okay, so this is Zeno, and this is anti-Zeno. But what about the Zeno arrow paradox? Because what we have seen, and everyone has seen so far, is the Zeno effect on discrete levels or a set of such levels. But what about really the equivalent of an arrow? Well, we predicted that this might be possible, that you could actually not completely stop but at least slow down considerably a particle in free flight if you correlate its internal state with part of the wave packet width, which means that suppose I have a probe or a detector that probes the internal state of the particle, and therefore if you in the course of observation flip the state from 0 to 1 and say they are degenerate, so no energy or momentum are exchanged in the process, and yet the bulk of the wave packet is now correlated to state 1, and the tails, which are outside the observation region, are correlated to state 0. And since these are orthogonal, the tails and the bulk stop interfering. And if you repeat this at the right rate, you can effectively confine the wave packet to the region of observation. And that is without exerting force on the particle, at least not on average. It's only an exchange of information, although, as I stress, in all these effects, you don't actually have to read out the measurement effects. It's enough that you single out the desired degrees of freedom. So we are really thinking about an experiment in which a photonic wave packet will be able to traverse a cavity undisturbed or be strongly slowed down by the presence of a detecting atom. And another poem that I have in the book summarizes this issue. It's called Zeno's arrow. Achilles, mighty athlete, is so vain, he gives the turtle head start as a bait, but lo, their distance measured time and again dooms them to an eternal stalemate. The mystery of space and time unfolds as arrows are launched but would not fly, only because someone their course beholds, and nature hastens with the observer to comply. So this is really an expression of the wonder, the sense of wonder that may be aroused by the fact that observations can actually affect physical observables. And on a, here, I forgot that I had this animation. So this is basically what I was trying to say. On a lighter note, what we have in the book is an illustration of this scenario under the heading, The Wedding That Never Was, which shows Henry Barr, who you may remember is a quantum wave packet essentially, and he's trying to marry his beloved, sweet Eve, by moving down the aisle coherently as a wave packet, okay? Perform a coherent transfer. And he says, my love, Rabbi will unite us swiftly. But when he starts to approach her in this fashion, as soon as his tail, 1% of him, reaches his beloved, it stops, the process stops, and this tail vanishes, and he realizes that this is because he's being photographed, okay? And photographed at the right rate, obviously, and this is done by the evil clone that is trying to prevent this wedding. But his beloved thinks that this is because he is having a second thought about the wedding. She does not believe in quantum measurements. All right. So this is the evil clone's summary. Zeno is brilliant. It will earn me the Nobel Prize I've long deserved. Well, that remains to be seen. So I've reached the part of discussion, and I would like to summarize the story I've been telling by saying that first, physics could never claim to be about reality. It was always the perception of whatever is out there through the mental filters of observers. And quantum mechanics is no exception. It probably is even a stronger case for this because it has contextuality that makes it even more observer dependent. And there is this strange situation in which information from observations in both thermodynamics and even more so in quantum mechanics affects physical variables such as temperature, work, or motion. And the strongest claim is that the time error of an open system is reversible under sufficiently frequent control and observation. So a mystery remains, which is who has this information? What is it? And I would say that, to me, this is something that, as the forefathers of quantum mechanics believed, Schrödinger, von Neumann, Wigner, this is the effect of consciousness, okay? And I define consciousness as the ability to create, and you may add, share information, okay? So I view it as a collective property, not as a property of individual observers, but of all observers in total. And they need not be human. I would say that all forms of life, because all of them, by necessity, observe and therefore affect the world, all forms of life, from cells to scientists, have some degree of consciousness, okay? Furthermore, there are no physical phenomena or laws without the consciousness, at least of scientists, okay? And Michel Houellebecq put it very poignantly by saying that, in fact, there's nothing but magnificent entanglement, which means that only our interrelation and exchange of information can be deemed real, not the rest. So I could go on with philosophical discussion, but maybe I will stop at this point and take questions if you have them. So thank you very much for your attention.
Yeah, thank you very much, Gershon, for a fantastic journey on the role of observers and observations. Yeah, and I'm sure that we will have many questions from our audience. Camille, will you assist us in guiding us through the questions, please?
Yes. So there's the first question, which is, what about blind people? Do they affect less?
No, not less. No, let me stress again that I am talking not about individuals, because then it would be really solipsistic, right? This is, you don't have to be blind. Eskimos, actually Aborigines, Australian Aborigines, believe that if you shut your eyes, then the world is gone, okay? But this is not what I mean. I mean what is perceived on a conceptual level, okay? This question goes back to what Wigner called my friend, okay, or the friend of the observer, okay? So it's someone that is able to get information not directly from the measurement, but from the observer that observes the measurement. So the friend asks the observer questions, and from those questions, he may deduce the results of the observation. So as long as there are data available, they affect the world, okay, to some extent. And this is, there may be degrees of affecting the world more or less. This is, we're not so far yet, but in general, I would say that any process that creates information which was not available before and is able to share it is part of this observer's effect of the world. So one should not take it as a personal issue. It's much, much more general than that.
Okay, thank you. So I don't see more questions for now, but maybe I can ask one. So yeah, maybe it's more related to the first part of the talk when you were mentioning the many words interpretation. And so, yeah, each time I hear about this many word interpretation, there's always underlying the assumption that the world, the universe is evolving unitarily.
Is what?
And it's evolving unitarily. Evolving unitarily. If you don't have unitary evolution, then you cannot reach to this conclusion. And yes, can you hear me?
I can.
Hello?
You don't hear me?
Yeah, now I can hear you. Yeah. So
yeah, we can. Thank you.
Yeah, it might be some issue in my internet connection. So yeah, did you manage to hear my question, or should I repeat it?
No, not the question. Only that you said that the underlying assumption is unitarity in Everett's.
Yes, yeah, true. So now the question is what disturbed me a little bit in that is we know that even if you take even an atom, it's never isolated. So you always have interaction with something else, with the environment. And so when you take a bigger system, you can expect a bigger interaction with the environment. So to assume that you can have a unitary evolution with the large object and even with the universe, I'm not saying that it's not true or not, but it's I think it's an assumption which is not so often discussed and yeah. So I wanted to know your point of view on that.
Okay. So look, I am not a fan of Everett's interpretation because he makes, not because of the unitarity assumption, that is fine, but because he separates the observer from the observed. He does not discuss the observer at all, okay? That's my objection to it. But unitarity is applicable to very complex systems, as complex as you like. And this is what I was showing, that you really are able to address this entire complex as a whole, or you isolate the object that you're interested in, again, by observations and control, okay, from the environment, and then it behaves unitarily again. This is the essence of the Zeno effect, okay? But if you are able, and we claim that you are able to act on the bath as well, on the environment as well, and then you may turn the entire complex, no matter how large it is, you may turn it into a quantum object which acts in a reversible fashion.
Okay, yeah. I guess maybe the right question or notion is maybe the time scale also of the observation. If you manage to monitor your system at the time scale much lower than much smaller than the time scale it interacts with the back, then the approximation of unitarity should be fine.
That's not even necessary. Of course, if you are able to do that, that's one way of doing it, but it's not a must, because what you can do is you can purify the bath, okay? And purify the bath, then forget about time scales. You don't have to act on very fast time scales. Then you just let the system in the bath interact with each other as they like, okay? Then it is guaranteed that everything will be unitary and reversible, okay? So it is really more about control resources than time scales. And the resources are in principle there. Of course, things get more complicated as the environment becomes more and more complex. But in principle, there is no line which clearly separates unitary from non-unitary evolution.
Okay, thank you. So we have some more question now. So another question from Arukuma Bisham. So information comes to us through dreams also. Does this also affect things like temperature, etc.?
Yes, the answer is yes. But of course, you need some kind of interface between the brain and the outside world, okay? But it is at your disposal, at our disposal. We have to build proper devices to do that. But these devices are still dependent on their ability to gather information, which in principle is something that we expect to belong to the inner sphere of our consciousness. But the point is that there is no clear line to be drawn between the inner and the outer sphere.
Okay. So there's one more question from Laurent Querela. So it looks like black magic because Maxwell's demon could be raised from death again. Or do I miss the main argument? Yeah,
Of course, this could be very hard at present. This is not something we can imagine, but physiological processes should be reversible as well if you control them sufficiently fast. We are very, very far from such a possibility. It's not black magic because at least it is formulated in physical terms, but it is definitely very awkward, okay? And Maxwell's demon is all of us taken together, okay? It's not some kind of super being, yes? All of us, all of science is about gathering data and processing them and manipulating them. So my point is that the ability of information to affect the world is really beyond imagination, okay? It's just a matter of technical possibilities, and they are, of course, limited by necessity, but they are improving fast.
Okay, thank you for these answers. Yeah, I don't see more question.
Okay, then Gershon, I'm looking at the time, and then we managed to finish perfectly on time. So I would like really, in the name of all of us, to thank you really very much for the very interesting talk, which will give us a lot to think about during the festive season. Yeah, we will have to think about the role of observers, observation, of consciousness, life. Yeah, those are the thoughts for the festive season. Because I guess if we keep going, we could probably discuss the whole night. Yeah, and probably we'll have as many opinions as participants in the colloquium. So Gershon, thank you very much.
My pleasure.
Good afternoon.
Let's go.
We will read carefully your book and
Any further questions, please feel free to contact me about them. All right?
Definitely, we will, because these are questions that interest all of us, and there is quantum everywhere, maybe even in consciousness. So we don't know. So we will find out. Yeah. Okay, Gershon, thank you very much. All the best for the festive season, and stay safe in your part of the world. Yeah. And participants, stay safe in our part of the world. Yeah?
All right.
So thank you very much.
You.
Enjoy your evening. Thank you very much.
Yes.
Bye.
Yeah, bye.
Bye. Thank you, Camille. Thank you, Ilya. Thank you, Gershon.
Thank you.
Yeah.
Bye.